So within the Mars Ice House concept, we introduced a vertically oriented lander that lands on the surface of Mars. We introduced two redundant ice shells that are 3D printed on the inside of an inflatable precision manufactured we said it would be an ETFE membrane. And then from there, we introduced programming that sort of expanded from this central vertically oriented lander. And I will show you some of these areas now. So at the very top floor, we introduced a wardroom and a galley. And we introduced a concept for vision windows where we can have thinner parts of the ice shell where the astronauts can look out to the Martian landscape. Here's a view of Ice House from the outside with a connection to the rover. And let's see, this is showing what we conceived of to be the IBO, so the ice printing robot on the inside of the precision manufactured membrane, how it would actually go up and scale the inside of this inflatable membrane by printing consecutive rings that it could climb on top of. So it would essentially deposit the water ice as vapor, and it would cool on impact. We did some very preliminary kind of benchtop testing for this, and thanks to some collaboration that we did with McGill, we're able to produce small scale ice prototypes. But all of those included a binding material, so we weren't able to push the 3D printed ice concept much further at that time. Very fortunately for us, after winning for the Phase 1 Centennial Challenge, we were able to be connected with a principal investigator at NASA Langley, who was interested in our project, but instead of pushing towards the additive manufacturing component of the narrative, of the 3D printing component of the narrative, was interested in how we can introduce a more feasible concept in a shorter amount of time, shorter term kind of time frame. So instead of it being 3D printed, it would be a filled and frozen ice habitat. So together we came up with a concept essentially for vertically oriented ice shells that would be inflated and then filled by water ice, ISRU, which is in situ resource utilization water ice. And we came up with a program for the interior of the habitat where we have multiple restraint, bladder, and scuff layers for the inflatable, and we introduced an open floor plan that could be adapted, or I guess you could say adopted, to any number of missions over on the surface of Mars. This is a section showing the interior of Ice Home and some of the limited programming that we did for crew habitability. And very fortunately, we were able, thanks to some additional funding that we received, to do some very basic benchtop tests to validate that filling and freezing ice within inflatable bags is a valid concept for a habitat. So here we Tess Caswell, who was a researcher that we worked with, who was at Brown at the time, was working within a Lamont laboratory, and she was able to fill and freeze water ice within Tedlar bags within a vacuum and validate that the ice grain that you see in this SEM imaging was actually mechanically strong enough to be self-supporting within the shell. This was also there was also research done internally at NASA Langley, where ice was again filled and frozen within Tedlar bags with a number of kind of fittings at the top of those bags. So some of them were plastic, some of them were metal. And as a result of some of these experiments, Mars Ice Home and some of the materials that were experimented with for Mars Ice Home were chosen to be part of the MISSY science experiment. That's the Materials in Space Science Experiment aboard ISS. This is a view of Mars Ice Home, the interior, where we showed a greenhouse concept on the second floor. As a result of that, just I guess you could say insinuation that there would be a greenhouse within Mars Ice Home, that we were able to be asked, myself and my colleague Christina were asked to serve as organizers for NASA's Big Ideas Challenge. And this was also a collaboration with NASA Langley, where we essentially took the concept for Ice Home and used it as a basis to conceive and to put together a competition where student teams could think about how to introduce the deployment and concept of operations for a Mars greenhouse. And there was some really amazing work and proposals that resulted that resulted from submissions to this competition, and one of them was worked on internally at Langley afterwards. So now I'll tell you a little bit about the Phase 3 NASA Centennial Challenge for a 3D printed habitat. Our version 1 submission, which is what you see on the left.
I'm sorry, can I have a question, please, before you pass this part?
Oh, yeah, absolutely.
I'm Elif from Turkey. I have a few questions, actually.
Hi.
Yeah,
sure.
Hello. My question is about not actually designing and so on, but I really wonder about the working area of space architects. As you know that I also try to expert about space architecture, but I'm really new about this. But the thing is that when we let's say, for a space architect, where is the land of working? I mean, we only follow the competitions, or I can maybe simply explain like this. On the Earth, when we try to do a project, we just talk to owner of the land, or we talk to municipality and so on. But when we talk about space architecture, designing on Mars and Moon, who is the one who are between me as an architect, space architect, and the land of Mars and Moon and so on? Did you get my question?
Yeah, I guess the way that I would address that is that terrestrially, like when we're doing traditional architectural contracts here on Earth, we have a client that we usually are working for, or there's a building owner, and there's a very structured relationship in the way that happens. Like an architect is providing a service to the owner, to the client, which then goes into the hands of a contractor, which would then be built. So there's a kind of defined relationship there. It depends, and I think that the landscape of space architecture is changing now that private entities are coming more to the forefront of the conversation of how do we introduce sustainable settlements on the Moon and Mars. In the past, it had been that I think it was really only internally at NASA that space architecture was a thing, was like a job and was a thing to do. And certainly there are many examples of prolific space architects who've gone through NASA Johnson, Human Habitability Division, NASA Ames, and been internal to the centers at NASA doing the work that they do. I think that is soon changing. Again, now that the landscape of space development and developing on other planets is commercializing and is growing. And I think that we're going to see more and more that private companies are looking to designers, and they're looking to design thinking and design innovation for how they can really infuse the value of their brands and infuse the experiences that they're going to be providing for space travelers and for for their customers.
Yeah, thanks a lot for that answer, but I have still
does that make sense?
Summed up. yeah, the answer is clear, but I have still a little bit doubts about something really. The thing that I wonder is, we don't all the time design for the space like we design on the Earth. Every day, every moment we need something to design for the Earth, but the space architecture is limited. We don't every day move to there every year or every century and do something. What I mean is that we design a lot of things, but still nothing constructed. So we design for what? I mean, is it like a I don't know. There are few architects. Maybe they will be enough for the space designing.
I'm gonna go back to one of my earlier slides to talk about this. You're right that there's not an immediate need for a space architect in the same way that there's an immediate need for an architect designing low-income housing, for example, or an architect might satisfy a need to fulfill a certain role in developing a master plan within a developing city, or a city that's just kind of getting off its feet. But I think that, and I think that this is what makes the field so interesting, is that it still has one foot in speculative process and speculative thinking, and one foot in realizing actual technologies. So it's a little bit of both. We can't say it's one or the other. Certainly, if we think about this in terms of like the economies of space architecture as a practice, no, it's not commercially profitable for anybody. You have to remember that Mars Ice House, not Mars Ice Home, Mars Ice House, the Deep Space Ice Home, Mars X House, the Mars Greenhouse Competition, and the second Mars X House, these were all done as a result of either a competition, meaning it was unfunded work, or it was work that was supporting another competition or an academic endeavor. So none of this was being sponsored by a direct client. Fortunately for us, we were able to have our first like major aerospace client, UTAS, which I'll tell you about a little bit later, where they were looking for us specifically as design consultants and to contribute design thinking to their processes. But it's very rare. And I think that it's still a developing concept for aerospace industry's giants to look to designers for consultancy advice and to bring new value into the work that they're doing. But it's changing. Like Blue Origin, I know for sure, has architects on staff. SpaceX has been working with industrial designers for many, many, many years. Even though it's a very small and limited team. And this is all going to change exponentially in the next decade or two.
Okay, thanks a lot for the answer. I don't want to interrupt more than this. I have other questions maybe in the Q&A part I can ask again. Thanks a lot.
Yeah, definitely. So yeah, I'll tell you a little bit now about Mars X House version 1 and version 2. Version 1 was won 4th place, and this was for 60% design, which was kind of a design checkpoint within the phase 3 3D printed habitat challenge. And then Mars X House version 2 on the right won 1st place for 100% design. So this is a rendering of Mars X House, which won 1st prize in phase 3 of the challenge. A view of a rover approaching Mars X House. And since we were collaborating with APIS Core at the time, together we came up with a redesign of their current printer on a mobile platform to show how and here we're showing how the exterior regolith shell would have been constructed. And here we're showing how the interior high density polyethylene layers would be constructed. And I'll tell you a little bit about the material system for the habitat in just a bit. Here though, what you'll notice is that we're showing on the upper right corner a deployed mechanical core, and we're also showing the high density polyethylene being printed. We started off with this idea of a deployed mechanical core because it was essential for us to incorporate the ECLIS, which stands for Environmental Control and Life Support Equipment, as integral within the habitat concept. So within this core, the ECLIS would be pre-integrated, mechanical equipment and hardware would be pre-integrated, such as experimental modules. And this was our main concept for how this could all happen autonomously and be deployed robotically. This is a view of the crew quarters on the inside of X House, and a view of the wardroom on the upper level of X House. This is a construction simulation where you'll see different parts of the X House project being constructed. So we started with a regolith foundation. First, we wanted to 3D print the high density polyethylene layers. The windows would be emplaced within the polyethylene layers first. And then the regolith shell would be 3D printed afterwards. So this orange is the regolith shell. We also introduced two types of basalt fiber reinforcement, circumferential hoop reinforcement, as well as diagonal reinforcement. And here you'll see an expanded view of the walls, the composite wall from Mars X House. So you'll see on the far right, we have the high density polyethylene layers. This is to ensure that we have an adequate radiation shield. We have adequate radiation shielding for the astronauts. Polyethylene is a very good shielding material for passive shielding against radiation. And it's also safe to come into contact with and safe as an interface material for the astronauts. Regolith, unprocessed regolith contains toxic perchlorates, which we know are going to be hazardous to human health, and we know that the astronauts should not come into close contact with. So we introduced the polyethylene layer as a way of creating that barrier between the unprocessed regolith on the outside and all of the hermetically sealed components on the inside of the habitat. We also introduced an expandable polyethylene foam, thinking about expansion and contraction of the material layers. And also, as I mentioned to you before, continuous basalt fiber reinforcement that would go in the diagonal direction, as well as the circumferential hoop reinforcement direction. And then on the far outside is the sulfur-based regolith concrete. And there you see it again. And this is going to quickly show a small portion of the habitat and what the construction sequence would be. So first the foundation is printed, then the polyethylene layers, then the expandable foam, first layer of sulfur concrete, the reinforcement, and then the final layer of sulfur concrete. This is a 3D printed model that we created for Mars X House, and this is on view, or at least it was on view, at the London Design Museum for the Moving to Mars exhibit. And this and the next video are showing, thanks to a residency that Search and APIS Core received within the Autodesk Build Center in Boston. This is showing basically how we 3D printed for construction level 2 of the phase 3 competition. And essentially what they asked us to do here is to 3D print this, what we called a water basin, and to robotically emplace, meaning lift and lower 2 pipe elements, the small pipe and the big pipe, within the 3D printed structure over the course of the construction sequence. Even though this seems like a relatively simple thing, there were many problems that came into play. And this is just the beginning of how NASA and other companies are starting to think about robotic construction and how to integrate the emplacement of other elements within 3D printed structures.
So how much time did it take to, sorry to interrupt, so how much time did it take to complete this structure by the machines, by the robots?
This structure, oh my gosh, I think it was, the total construction time was something like 7 hours. 7 hours, yeah. So you see it sped up a lot in these videos. So after we finished building the structure, it cured overnight, frankly, because we had a deadline to meet. And then we filled the structure up with 20 centimeters of water. And this was sufficient for us to win first place in the challenge. The idea here was that they wanted teams to demonstrate that 3D printed structures can actually be watertight, ahead of thinking about how they can be airtight to contain pressure and constant temperature for a sealed habitat. I don't think any of the other teams, to my knowledge, were able to create a watertight barrier without caulking and sealing the structure manually, but we did none of that, and very fortunately for us, this was sufficient for us to win this part of the competition. And now I'll tell you a little bit about our first real commercial contract with an aerospace company. And this was United Technology Aerospace Systems. They had seen our work on Mars Icehouse and some of our work afterwards, and they were very excited about the possibility of bringing designers on to think about how we can reimagine some of the hardware development that they were doing. So they came to us with this idea that, you know, they wanted to introduce a more I guess you could say coherent concept for how their hardware, their ECLIS hardware, which again is environmental control and life support systems hardware, could integrate with a number of habitat providers that are providing designs for NASA's Gateway program. And the project is part of the Next Step initiative, where NASA reached out to multiple aerospace companies to come up with habitat design concepts for Gateway and also for transit vehicles to Mars. So this essentially their hardware is broken up into multiple pallets. These are kind of like lockers to house and contain all of the hardware that maintains the temperature, waste management, temperature, air, pressure, waste management, and water management aboard the vehicle. So these are on the left, you'll see the deep space habitat providers. Each one of those was coming up with a concept for a deep space habitat, which could be incorporated in Gateway, but also in missions to Mars. And on the right, you'll see our final design that we introduced for UTAS, which essentially introduced a faceted front panel on the ECLIS pallet, as well as a removable handle that could be installed and deinstalled on that pallet. And you'll also see that Dan Burbank, who is a former NASA astronaut, was able to come in and sort of test and evaluate and review the ergonomics of our design. Ultimately, our design introduced more interior volume for the hardware and improved the mechanical strength of the design because of these facets. So this was a value add that we introduced to their, I guess you could say, systems engineering process that hadn't been there before. So you'll see on the left, that was the hardware that we started out with, and then on the right, this was one of the habitat visions that we put together. And yeah, that's basically the UTAS project. Now I'm going to tell you a little bit about our current project, like what I'm working on now. And this is the Moon to Mars Planetary Autonomous Construction Technology project, which has been initiated by NASA Marshall Space Flight Center and is a collaboration amongst private and academic partners, such as Icon 3D, who is our client at the moment, and other industry as well as university partners like the Colorado School of Mines. Icon is the first U.S. company to have a permitted additively constructed house in the United States, and they do lots of work for development of homeless shelters and homeless housing, and frankly, they are leading the way in developing 3D printed concrete structures terrestrially, and I believe have printed the most number of structures in Austin, Texas, and in Mexico out of any construction design build company in the world. So together we were connected through NASA Marshall, and we put together a list of requirements for Earth-based as well as lunar-based construction, and we were interested in introducing dual use benefit not only for terrestrial construction but also in the long term for space. So this led to a set of shared functional requirements to benefit the goals of NASA, Icon, the Department of Defense, and Search. So below you'll see some of the requirements that we came up with for the autonomous construction system. Some of these have to do with design for field repairability, dust mitigation, shielding, ballistic protection, and the list goes on. And the overall goal of the MPACT project is to demonstrate autonomous construction technologies on the surface of the moon in an effort to introduce a permanent settlement and a permanent lunar outpost on the moon within the 2026 decade. So first, we're going to start to develop horizontal structures such as landing pads and roadways. And then eventually we will start to develop collaboratively vertical structures, so habitats, blast walls, and other infrastructure elements on the moon. This is going to be a long process, and it's going to take a lot for us to get to where we need to be, but the first real milestone is planned to be the demonstration of a 3D printer of additive construction payload, I guess you could say hardware, within Eclipse lander, which is a commercial lander on the surface of the moon. And we recognize that 3D printing is possibly one of the more challenging building construction concepts relative to creating a sustainable presence on the moon. We know that there are simpler ways of doing this, and yet we're very committed to the development of additively constructed structures because we feel it's going to lead to exponential development of lunar infrastructure and eventually Martian infrastructure using only the resources available on the planet, which is something that we cannot do and that would not be sustainable using our current rocket propulsion technology because it's too expensive, prohibitively expensive to launch everything from Earth. So even though we know that we can launch, for example, what's referred to in research as a class 1 habitat, so a hard shell habitat module, or an inflatable habitat that deploys on the surface of the habitat, we are very committed to developing 3D printed structures on the moon and Mars because it is going to lead to, and it supports the vision of a long-term sustainable presence on that planet. And this is a kind of sneak peek of some of the design work that we've been developing with NASA and with Icon 3D. So here you'll see some of the landing pads that we've introduced. And that's what I have prepared for you. Oh, good. And there's still some time for questions, which is